All right, let's get started. Thank you for joining us today. I'm Genoa Stars. Today we're going to be talking about geospatial Python, but in open source packages and open source methodologies for processing spatial data. I really love this topic. I work with a lot of spatial data in Python lately, although historically I've worked with mostly R instead. And so transitioning to Python has been a really interesting process, but there's some really great packages and it's been a really fun experience. Can you guys see my slide okay?
Yep.
Perfect. Okay, let's go. So I think the two of you on here have been on the previous few calls, so I'll skip over these UCANR slides. But yes, we are the Informatics and GIS program with UC Ag and Natural Resources. And we have a wonderful team, and we're happy to be here with you today. And today we're going to cover a few things just to get started. What is open source? What are the softwares we're using? What's the data sets? And what's kind of the overview of the geospatial workflow? And then we'll skip straight into the coding. It's going to be a pretty hands-on day today since Shane did such a good job covering a lot of these topics in the ArcGIS ecosystem last week. So open source means that the language, the coding language itself, which is Python, and a lot of its associated libraries or packages have a license that means it can be distributed, modified, and used by anyone for free, which is pretty cool. So people like us can use all these tools that have been developed by other people, including professionals and companies, amateurs, and scientists. It's kind of a wild, wild west out there. But Python is one of the most widely used languages, which means it has a lot of people generating packages and libraries all the time. So some of these advantages are that there's a huge diversity of available tools. If you can think of someone's already said, I wonder if I could make a package to do that, which is pretty handy. There's competition in this sort of system. You have people developing packages that accomplish the same tasks. So that means maybe one is better than the other for your purposes, but you're not just stuck with one option. There's a lot of transparency. You can often access the code that shows how these tools work and see exactly what they do. And there's a lot of opportunity for collaboration and community. There's other people out there like us doing data science projects, wrangling data, thinking about the same kinds of problems and how to best handle them. Some of the disadvantages are that there's sometimes a lack of quality control. I don't think there are many places that kind of maintain packages or quality or standards for them, but there's also people who just kind of post whatever they want up and out there, and you can find those by accident or on purpose. And some tools have really good instructions and documentation, and others don't. This is pretty different from the ArcGIS ecosystem we saw before. Most of the packages we used in there, they built off of very common Python building blocks like NumPy and Pandas, but then all the ArcGIS and spatial functions are controlled by Esri. Like they wrote those, they have teams that maintain them, but we don't get to see how they operate or what code they explicitly use. We will be interacting with kind of the Python world using Anaconda Navigator. Now, it seems kind of clunky, but this is a tool that helps keeps your distribution of Python up to date. It helps you manage the environments and what packages and libraries you have. And it sounds kind of silly, but it gets pretty crazy when you have a lot of different installations of software, and they can actually interrupt and break each other if you have different installations going at the same time or different packages that conflict with each other. So Anaconda Navigator is a really nice kind of point and click way of handling these things and keeping them straight so that you can focus on achieving the tasks that you actually care about. It's a solution for people like me who are not very comfortable with the command line. And that's, the screen they use in all these science fiction movies where they're hacking, where the screen is black and there's like flashing dashes and things like that. It's not actually that complicated, but if you're not a computer scientist, it can be a little bit beyond what we're comfortable working in. So Anaconda Navigator, thank goodness we don't have to deal directly with the command line. It helps you create new environments and see what's in them. And it helps us interface with some of the other development environments like Jupyter Notebooks, which we worked with last week, Jupyter Lab, and things like PyCharm that help us code and develop our own programs. Jupyter Notebooks we met last week, open sourced integrated development environment that lets us create and share our code. And in this case, it's also going to provide visualization support so we can create maps and graphs and all sorts of things that we can see in our document. And I can easily share it with you guys so you can implement exactly the same code, which is really powerful. Finally, we're going to be using the same data as last week, but we're going to be accessing it slightly differently since we're not interfacing directly with ArcGIS products in this workshop. You should have downloaded the GeoPython session 3 folder from Google Drive, and then just unzip to the main shell folder, and it'll contain our data sources, one of which is an Excel spreadsheet, one is a zipped shapefile, and one is a geo package. And there's no particular reason for these formats, except for we want to show you how to interact with each one. And if you don't have access to that folder, let me know. I can paste the Google Drive link in the chat. Our main objectives in here are to be able to import and read spatial data in our open source Python environment, to know how to check our projections and transform data sets to match, be able to combine spatial data sets and perform some sort of spatial analysis. So in this workflow, I've included clipping, buffering, spatial joins, and I think one more, we'll see. And then be able to write a function to automate a chain of simple spatial data operations. And I'd love for you guys to feel excited to apply some of this information and these strategies to your projects. So that being said, let's get started coding. I'm going to close out the slides here, and I'm going to share my screen as I work into Anaconda Navigator. And hopefully everybody's still with us at this point, but let me know if you have trouble following along in any of the steps. Paste it in the chat. We've got Shane and Andy and Robert in there, and they'll be able to help you if you get stuck. So first step, we're going to open Anaconda Navigator. This is my home environment. You'll probably, when you open it, it'll come up as base. So if you did create your environment yesterday, it takes a second to change environments. Go on in and find your way to the environment you created for this training. It's got a lot of packages in there right now. It's thinking. Is everybody still with us so far? How's it going? Okay, now that my environment is loaded, I'm going to go on in and find my way to Jupyter Notebook, which I installed yesterday, and I'm going to click the Launch button. And what it actually does is it opens a browser window. My default browser is Google Chrome, but it should run it in any browser that you choose to use. Once I've gotten in here, what it actually shows me is my user drive from my computer. So the C drive, the user, and from there, I can start navigating to the folder that we downloaded yesterday. So is anybody having trouble? You can unmute and say so, or post it in the chat just to check in. Hopefully that means things are going well. Okay, so from here, I'm going to go ahead and navigate to the horrible location that I saved the folder for this workshop. Hopefully you guys did a little bit better, but here's my unzipped GeoPython session 3 folder. And inside there, there's my zipped data folder. We're going to leave that alone. And then there's the GeoPython session 3 IPyNB. So that's a Python notebook format. And we're going to go ahead and open it. It should look very similar to our Jupyter notebooks from the other day in ArcGIS. But yeah, we're running it directly through a browser this time instead of through our Esri ArcGIS Online with all the extra fancy sidebars and toolbars, etc. Can everybody let me know if they've made it this far? Either through unmuting and just saying, oh yeah, good, or a thumbs up in the chat. Just want to make sure. Can everybody hear me, just to check?
Yeah, I got it.
Yes,
Okay.
we can totally hear you.
Cool. Great. Okay, sounds good. Thanks, guys. Okay, so here is our Jupyter notebook for this workshop. Housekeeping. Again, you can use Control Enter if you're on a Windows machine, or Command Enter to run a current cell, or you can hit the little play button up here. Or you can use Shift Enter and that'll run the current cell and move you to the next one. The first thing we're going to do, since we're in this new environment we created just for this workshop, is install all the packages we need. So it seems like a lot of packages. That's because we're doing a lot of things that aren't created by one person. So we're putting a lot of pieces together, but a lot of them just do kind of small little tasks. So we need a few more of them, but they're not necessarily big or heavy pieces of software. So pip is a package manager in Python, and the exclamation point tells it we want to talk directly to the environment. And we're going to run this cell, and you only need to run it the first time you're doing this notebook. See, I have run it recently, so all of these have already been installed for me. But if you're starting from your blank notebook, you'll want to run this cell, and it might take a minute or two, but it's going to go ahead and install all the packages we need. Kind of nice. It makes sure that all the things it needs in the package are also installed. This is like we're kind of building our library, our big building full of tools that we're going to use in this project. And then after that cell has been run, the next cell is what's going to kind of say, these are specifically the tools we want for this notebook. And we'll go ahead and run that one too. Beautiful. Since you folks were in the last session, I'm not going to spend a lot of time in this tabular data part, but again, we have instructions on how to read in help information for certain packages using the question mark or the help command. We have reading in our folder, and this I'm doing slightly differently than we did that in the last session. Here, I'm going to ask you to replace the information in this session 3 folder zip with where you've saved your session 3 zip folder. So in my case, I would go to the folder I downloaded for this workshop. So GeoPython session 3. And then for the session 3 data folder, I'm going to right click on it and copy the path to the zip file. As you can see here, it's the same as the path you see above. But you go ahead and do that, and then without deleting the R in front, go ahead and paste that path here so that it'll open the right folder for this workshop. Unlike in our ArcGIS Online environment, our data is directly hosted on the computer for this workshop. And the handy thing we're going to do here is save the information about the folder where all our data is. So every time we open data in the rest of this notebook, it will start by looking in that folder. So go ahead and let me know when your packages have been installed and when you have pasted and run this unzip folder path. Can you guys do that? I'm also going to use a print command here to make sure that it pasted the right location for the data. This step opens the data folder, unzips it, and then saves it as a folder without the .zip. So that'll be our main directory for this project. We've already gotten through the unzipping step right here, where we found our folder.
Yeah, that worked.
Awesome.
Yes.
Ah, excellent. All right. So next, we're going to only tell it the name of the Excel file, which since I gave it to you in that folder, should have this exact name. And then here we use F So F outside of quotation marks says that anything in brackets is an object. So we told it what session 3 folder is, right? When we unzipped our folder. So here we're saying, okay, this is the Excel file and this is the session folder. Add them together and then open up that file. So go ahead and run that and it should open up our Excel file. So this is just handy because if we ever change what our session 3 folder is or move it, if you just change it in this first chunk up here, everywhere else in the notebook, it will find the new folder. So I tend to write my paths that way. So here we go. We're using pandas, PD, read Excel, and then it's opening our Excel file as UCANR locations. And here we can see the first 5 records in our database, which is addresses of University of California Cooperative Extension offices in California. So we did this step last time in ArcGIS. And again, we're going to do a similar couple steps here. We're going to clean up the addresses a little bit. So we've got all these colons and the column names. We want to check for errors. The next cell fixes that. And then we're going to do geocoding using a tool called GeoPy in GeoPandas. And this is interesting for a couple reasons. First, it's going to use ArcGIS again, but without requiring any kind of login. I'm not sure how they negotiated the permissions for this, but I find it kind of fascinating. This cell right here, we'll go ahead and run that. This is what creates our full address fields. Most geocoding does require the full address to be in one column. So this is the same as Shane did in his notebook last week. And here we go. We're using this geocode command with provider ArcGIS. Other ones that they have include OpenStreetMap. And there's a couple, you can also try using Google as a provider, but it requires a key. I tried a few of them for this workshop, and ArcGIS did the best handling the addresses, which I thought was interesting. OpenStreetMap had trouble finding some of these locations. So I don't know if that's because they do the best, have the best database, or are the best at handling kind of these long strings of addresses. But go ahead and run this geocoding step once you've created your full addresses. And the other thing we'll do in this chunk is we'll check the CRFs that we get from this, because prior to this, it hasn't been a geospatial data set. It's just got address locations. And then we'll check the type of data frame. We didn't really do too much of that in the ArcGIS session because they're either a spatially enabled data frame or they're an ArcGIS file. Here, we're going to have a few different types of data frames. So here we can see we use the .crs after our data frame to check the coordinate system and print it. So it's 4326. And then right now, our data frame is a GeoPandas geodata frame. And this is going to be our best friend during this entire training. Geodata frames identify a geometry column, and that's kind of, they run all our spatial operations in this notebook, and they do a lot of the visualization as well. So we're going to want most of our work to be in this geodata frame format. Unlike some other formats, it does not care where your geometry column is or what it's named, but you do have to tell it what it is if it's not called geometry. So here we go. It looks like we have a successful geocoding, right? We have point data, we have our addresses, but we are missing our other information, right? We only retained those 2 columns. So here we'll use a command called merge to join our original data set, these locations, with our geometry. So here I'm using PD merge, and the first argument is which data frame do I want to add information to? The second one is what do I want to add to it? And these double brackets identify if I only want some of the columns. So here I'm telling it, I don't care about the address column. I actually just want you to add the geometry column. And I want to join them by the index because they are in the same order. Here we go. We're going to go ahead and run this, and we're going to check the data type again. So this data, now that we've run this pandas command, has everything we need, has the geometry, but now it's a pandas data frame. We will correct that in this next step. Surprisingly not hard, right? We're going to use a GeoPandas command, GPD, instead of just PD. And we're telling it it's a geodata frame. And you know, because we want the geometry column to be geometry. So let's just run this. And then we're going to have our beautiful geodata frame back, location, address, city, state, full address, and our geometry column. The other thing we're going to do here is we're going to remove any columns where we didn't successfully geocode. I think there's only 2 of them in here. And you can see they actually didn't have any information. They were just rows that were empty in the first place. So it's not really surprising that they didn't geocode successfully, but we'll take them out because in this next step, we're going to take a look to see if it was successful. Whenever I do spatial data, I have the need to see if the points are actually correct because I need to see it to believe it. So I'm going to use a really simple command here, and this is something you can do. It's GeoPandas plus a package called matplotlib in the background, and we are just going to type the name of our geodata frame, UCANR-IGIS dot plot. So that's pretty simple, right? In this case, it's a static plot. I included as well an interactive method, which is just this top command. If we put a hashtag in front of the plot and delete the hashtag in front of this one where it says .explore, we can see something really cool, which is that GeoPandas has a built-in integration with a package called Leaflet and Folium, and it can generate interactive figures, which I think is so cool. And this is something I think the ArcGIS platform can do as well, but I think it's just so amazing. You can use a simple command like this and then be able to scroll in, scroll out. We didn't give it any information about what we wanted to visualize, so it's just going to display our geometries. We can't, well, there we go. If you hover over it, it looks like it'll give you the rest of the fields. So, I mean, that's pretty amazing. And this is also primarily useful in a platform like a Jupyter Notebook. So pretty cool. And hopefully that worked for everybody. Now it's been a half hour. Does anybody have any questions at this point? I think we'll probably take like a 5-minute break, but I just want to do a check-in. Has everything worked for people so far? Does anybody have any questions? This is our geocoding and initial visualization section. Cool. Okay, let's come back at 1:35. So get a drink of water, go to the bathroom, but then we'll get started on reading our other data in from file. So bear with me. I think this is a pretty cool tool, and we haven't had to do that much clicking and dragging it, which is my favorite part. So, all right, see you guys in 5 minutes. Yes, Shane?
Oh, nothing. I was just clearing my throat.
Oh, no worries. Okay, it's 1:35, so we're going to pick back up. So, hey, Shane.
Hello.
I think, yeah, let's pick back up. So we're going to move into reading in the rest of our data. So accessing spatial data from file in GeoPandas, there's one main command for almost every file type, which is read_file. Handy. In session 2, we pulled in data directly from ArcGIS Online, which is a pretty cool capability. GeoPandas doesn't have the same level of integration with that, but we can use other methods like Google Drive or GitHub to access data. We can even download data from ArcGIS Online. We just don't have that live connection. An API would be another way to maybe access that. But what it does mean is that once we've downloaded our data, it's our data. Like you have control over exactly what's going in, when it gets updated, and you can save lots of other versions of it on your computer. So the first package we're going to read in, or the first file, is a geo package, and we're going to use read file. Read file has 2 main options for engine, which is the argument here. We're going to use what I think is PyOgrio, but it's actually PyOgrio. which is much less cool. And we're just going to, again, tell it the name of our file. Don't even need the R here. And then we're going to tell it to attach it to our session folder to make the path. And we'll go ahead and run that cell. So here we're also printing the shape. So how big is it? And the CRS, because we always want to check our projection. And then the head, so we can take a look and see if it looks good. So it's 751 rows, 15 columns, and it's in EPSG 3857. You can see here there is a geometry column. So again, this is all the UCANR academics and their physical locations. So these geometries are our point locations for these academics, and the locations are related to those from our initial geocoded file. Next, we're going to start mashing these together really soon. So we've got to open up some more spatial data right away. We're going to open our California County file. So we're going to tell it the path of the zip file. Again, then we'll join the two paths together to get a full one. We're going to create a new folder to unzip it into, just like we did with our first file. And then in the next step, we'll go ahead and read the file in. Again, we do have to specify the engine, PyOGRIO. The other one, Fiona, I find a little finicky. So if something's not working, if you didn't specify an engine and you're having trouble reading things in, I suggest switching to this one. So we're going to call it California County's Geodata Frame. We're going to check our CRS because that's what we do. And this is kind of a fun little argument. We're going to say, does the CRS of the California counties match that of our academic locations? So we'll print that statement and it says, yes, it does. That's great. And then we will fix the fact that county name is county NAM in the original data frame, just so that we don't have to remember whether it's county name or county NAM. And take a look. We've got our county shape files, and you can see here in our geometry column, very clearly labeled polygons, whereas in our previous one, there are definitely points. All right. Let's do a little bit more extensive mapping now that we have two layers to play with. First, we're going to name our map ANR locations basic, and this is going to be a really basic map, and we're going to use the explore command again on our geodata frame. And then here, we're going to add one more argument. We're going to say we want the color to be blues. So CMap usually means that the colors are based on some sort of value. It's a color map. We didn't tell it what column we wanted it to be based on, so it should just be one color, blue. But then we're going to go ahead and add our academic locations, again using the explore command. We're going to add it. M just says which map we're adding it to, our ANR locations basic, and we want those to be yellow. And then we'll go ahead and print our map. And there it is, blue and gold, beautiful for the UC system. So now we have an interactive map of our locations in their counties, which is pretty fun. And then if we go down one more cell, I'm not going to go into this, but I provided some fun mapping resources. I don't know if you guys are as obsessed with maps as I am, but there's lots of colors you can choose from, color maps, other arguments you can add. And for example, of what you can kind of, this is not the pinnacle of cartography, but this is a slightly fancier map. Here we can change the base map option. Previously it was OpenStreetMap. Now we're going to say we want to use positron. There's three options. We want there to be pop-ups when we click on objects in our counties. We're going to tell it we want the colors of the ANR locations to be based off of which location they are. And then there's an argument called tooltip that is what comes up when you hover, and we want the tooltip here to be the location. And let's go ahead and see what that looks like. You can also specify other style keywords. So here, we only want the counties to be one color, so we just said the color should be this. There's no color map in this case. We want them to be royal blue filled with light steel blue that's slightly transparent. So here's a slightly, arguably prettier map. Depends on your particular taste, but we've got our hovering tooltips here. And then if I click on it, it displays all the information from the data frame. And then the counties, when you click on them, tell you what they are. So kind of fun. Again, a useful tool. But this is only really useful if you have somebody else working in a coding environment or you're hosting a web page. You can also create static figures using matplotlib. And here we create a plot. So this is basically making a little canvas for a figure. And then similarly, we use the .plot command. We tell it we want it on this figure. And then specify essentially the same information. We still want the counties to be light blue with dark blue coloring. And then we plot our locations on top of them. And we want them to be the same color map. We don't want them to be outlined. There's lots of little things you can kind of fiddle with here. And then here, since it's a static map, there's some more options, but we're going to tell it we don't want axes for the map. We don't want like tick marks. We just want a title and a legend. So this is what a static map would look like produced this way. And again, nothing will happen when we hover over it, but it would be something you could produce for like a publication figure or slideshow. All right, so after that kind of side step, let's go back into some spatial data wrangling. Here, we are going to summarize information by spatial area, and we're going to do some other spatial analyses. So the first one, which we also did in the other workshop, is a spatial join, which merges data sets based off of their spatial attributes. So in this case, here's the command. It's GPD, so GeoPandas sjoin, handy for spatial. You have your geodata frame 1, your geodata frame 2. You tell it how you want them. Well, predicate and how are separate arguments, but predicate is essentially how. Do you want it intersects? Do you want it within? And then how in this context means which data frame do you want to keep all the information from? So we say here left, so geodata frame 1 will have all the information that geodata frame 2 will be joined to. If we said right, it would do the opposite. So the first thing to do, and I absolutely sound like a broken record though, is make sure they're in the same coordinate system. Here I've made it a little statement that actually just runs our Boolean again. Are they true or are they false? So it says if the coordinate systems don't match, project it to be the same. So that is this command 2_CRS. It's that simple. It's pretty quick, especially with our little vector data sets. And if they do match, we're just going to print this like supportive little statement. I need a lot of validation, so it's good to have something that just tells you the code ran. Okay. And then we're going to run our join. So we're going to create this new data frame, ANR counties, and we're going to do it using sjoin. We're going to join the county information to our academic location information. So we should end up with points, but then it's going to add what county and what county information those points fall within. So let's give this a run. All right. Looks like our projections were good. Spoiler alert, I did know that ahead of time. And I also printed here so we can just take a look the columns from the 2 initial data frames and then the columns from the data frames joined. So you can see we got all our location information from one, all the county information from the other, but we only kept one geometry column, which was the points. And then again, it relabeled the index column of the right-hand data frame from index to index right, because no 2 columns can have the same name. But we ended up with about what we expect. We have our academic information, so 751 rows, same number, but we've added the attributes of the counties that the points fell within. And our geometry is still point. Now, spatial joins are great, but there are other things that you can do with spatial data. These are some operations I use a lot. So first there's buffer. So this extends the geometry of vector data by the distance specified, and the units of the distance depends on the projection. I've included a link to the GeoPandas documentation for the buffer command here, which is pretty cool. GeoPandas is really, really well supported. So these are all other sorts of commands you can run: union, boundary, intersection, difference. It's a really powerful tool, and the ArcGIS API has many similar commands, but their documentation is, in my opinion, less accessible. So that's one really wonderful thing about GeoPandas. So here, I'm just going to use this double bracket system to only keep some of the columns from ANR counties. We ended up with a lot of stuff I don't really care about when we did this join: shape area, length, county number. It's not important to me. So I'm going to only keep the academic title, name, location, discipline, and county, and the geometry. And in this step, I am going to rename my geometry column location geometry, because these are the points of the ANR academic locations. Because in this next step, I'm going to be a wild thing, and I'm going to add a second geometry column to my data frame. So we're going to use PD merge, which is what we used for a non-spatial join previously, which again, we're not doing a spatial join. We're just going to add our county geometries to our location geometries by the county name. So we'll go ahead and run that. And you'll see, here we go. Oh my gosh, we've got our academic information, their locations, and then we've got both the points and the county polygons. So this is something that is pretty cool about geodata frames. You can have multiple geometry columns, and then you can also specify which one to use under various circumstances. So here, we're going to tell it that we want our geometry to be the point geometry right here. ANR geometries, set geometry, location geometry. And then we're just going to double check that we know the coordinate system. And then the other thing we need to check before we do a buffer is, what are the units of the coordinate system we're using? Because some coordinate systems are in feet, some are in meters, some are in miles, and then some of them are in arc seconds and degrees. So if you're going to tell it to buffer by a certain size, you need to know what unit it's going to assume that's in. So we printed this command .crs.axis info. And if you look in here, there's all the information about the CRS. But just here, you can see that our units are in fact meters, which is great news. Very familiar with meters, very comfortable working in meters. So that's the answer to our bonus question here. Our projection 3857 uses meters. So here we're going to, just for demonstration purposes, we're going to buffer by 30,000 meters. So here we tell it, for our data frame and our geometries, we want a new column called location buffer. And that column is going to be defined as when ANR geometries has point geometry, buffer that by 30,000 meters. So then we can print it, and we'll see we have a new column called location buffer, and it's a polygon geometry. But again, do we trust it without seeing it? Some people do, some people don't. I absolutely do not. So I'm going to go ahead and plot it. Here in this plot, I am using the same data frame because it has 3 geometry columns, and I'm just telling it each time that it's printing a different geometry in the plot. So that's kind of fun. And here we go. You can see here the dots are our location geometries, the counties are in light steel blue, and then we've got our buffers in green. Looks pretty good. The really pale ones, that's because there's fewer academics in those locations, and the dark green ones are because maybe there's 40 academics based in that spot. And there's a few counties that don't show up at all because they don't have any ANR locations. Excellent. The next spatial operation we're going to give a try is clip. So clip literally clips a vector layer to the specified extent, just like taking a pair of scissors and going for it. So by default, it just draws a box if you give it the information of the coordinates, but in this case, we're going to clip it to a specific county. So back to our ANR geometries, which is our absolutely insane 3 geometry table. We are going to tell it that we want to only keep records where Merced is the county, and then we only want to keep one of them. And this is going to be the extent of our clip. So we're going to say, like, we just need one piece of information for this process. We just need the shape of the county of Merced. And then here, we are going to run geopandas.clip, and we're telling it, okay, I want to clip my buffer geometries to the extent of our little Merced polygon. Okay, so we return this and we get a table. And I ran this for the first 10 records, but this is a hard question. Maybe Shane or somebody will have to answer this. Can anyone think about why the 10th record is not in Merced County? It doesn't have to do with the fact that it's the 10th one, but we have quite a few records in here that are not only based in Merced.
Let me think. Is it okay, Robert? It could be that Merced is a multi-county partnership. So there are people who are in Merced as well as Merced and Fresno. So
It's
that
an
might
interesting
be
thought.
it. Robert, what do you think?
I mean, Merced's not an MCP, but if it's an advisor, they have multiple county assignments, and Merced might be one of the counties they're assigned to, even though their actual headquarters is in a different county.
That's close. I mean, you guys are using real information about the real world situation. It's slightly simpler and more complicated than that. Does anybody else
Okay.
have a guess? Prakash?
Yeah, so like might be that like they have both county name in the list, so that's why it's confused.
Well, I'll give you guys a hint, which is that we just ran a spatial operation, right? And these were really good guesses. And this is a hard addition bonus question. But the answer is actually, I wonder if yeah, here we go. You can see these points that we retained that are outside of the county. Their buffers overlapped with the county. And what we clipped was the buffer geometry. So it kept those records because we only told it to look at the buffers, right? So if we had instead clipped the point geometry, we would actually only have counties, points in Merced.
Nice.
Kind of fun. Now we're thinking with GeoPandas. I'm a really big nerd, guys. So yeah, it's kind of cool. So it literally clipped our buffer geometries to the extent of Merced County. Yeah. And we take a look. The last kind of simple spatial operations I'm going to do are centroid and distance. So centroid generates a point at the center of a polygon, and distance measures the distance to a specified feature. So these are often used in like network analyses, things like that. Centroids are pretty common, especially when you're converting or thinking about polygons, but you only want a point data set. So again, these are pretty easy in GeoPandas. The command is centroid, and the other command is distance. So that's great. Here we go. And if you only have one geometry column, you don't have to do all of these set geometry commands, just to clarify. But in this case, we want to create a new column called centroid geometry based off of our counties. So we're going to create a centroid in each county. And then we're going to tell it that's what we want to use for the next operation. And then here, we want it to calculate location distance, a new column, and that's going to be for each row. How far is the point from the centroid of the county it's in? Let's go ahead and run that. This last section drops any duplicates of locations. So for this, we just get for each location, how far is it from the centroid? And here you go. We now have a new column called location distance. And then our centroid geometry is in here too. And if we run one more plot, we can now see the distance of ANR office locations from county centroids. So they are darker red the further they are from the county center. So maybe not the most useful example, but it's certainly a useful set of operations that you can chain or use to process your data. So kind of cool. I don't know why this office is here. That's pretty crazy. Must be a lot going on. Yeah, fun, huh? Okay. Is everybody doing okay so far? Have I lost anyone?
Nope.
Okay, cool. So we're moving right along here, making good time. Next, this is going to be a review section for you folks since you were in the last session, but we're going to replicate Shane's tabular data manipulations. So first, we're going to make a table to use in maps in the future of how many employees and how many job titles are at each location. So the commands we talked about last time, group by and aggregate and reset index, are all here again. And we can use that to say, okay, Yolo County has 4 different titles and 62 employees total. And that is still georeferenced, still a geodata frame. We're going to also get the count of academics per job title per county. So this is stratified one level further. So instead of just how many titles are there, how many people are in each title. And this kind of data wrangling seems kind of like fussy, but these are all objects that we are going to be able to use later in charts or in mapping, where you do need to have things in a specific format. And then finally, the real power command that Shane went into last week, pivoting. So creating new columns based off of other values. So here we're creating a column from each value, each academic name. Wait, no, we're creating values for columns based off of each academic, each unique academic, and we're creating new columns from the titles. Okay. So now we have this employee table, pivoted table. Matplotlib is the graphing package, one of the primary ones in Python. If you're more familiar with R, there are other packages like Plot9 and Seaborn that I've heard really good things about. But Matplotlib is kind of the golden standard. The syntax is just a little bit more different. And when we plot this pivot table, we get a plot, but we would like it to be a little bit more sensical. So here Shane has this operation that he wrote to sort it by total number of academics. So instead we get the beautiful stacked bar chart from least to most number of academics. So the commands here were per row, add the values for each job title, apply that to each row to create a sum column, and then sort it by the sum and drop that column, and then use that to make our table. Easy peasy, lemon squeezy. A lot of coding feels that way when you read it, but when you're writing it, a lot of it is checking how many parentheses you have, or if your commas were in the right place, or if your quotes are the wrong type. But now that we're done with all this data manipulation, let's have some fun. Fun for me, maybe fun for you. But this is how I think in my day-to-day life. Say I have a lot of tasks I need to do, and I know the chance that I'm going to do them incorrectly or that I'm going to need to repeat them with different data is pretty high. So in this case, say I am an administrative staff person in an extension office. I need to make a chart with the number of employees per position title, a map of the distribution of employees in the county, and an Excel file of a report of employees per title by location. So maybe I'm like writing a blog post or creating a series of profiles for each extension office. Let's see how we can create something that's kind of replicable and adjustable easily. So we're going to build a few functions here. The first one, sample function, is going to filter the ANR employee data frame to a specified county and return 3 things. Amazing. The polygon geometry for the county we said, the point data frame with employee and county information for our mapping, and then the pivot table we used to make the chart above. So here we go. Sample function it takes the California County geodata frame, the cooperative extension locations, the name of the county, and the distance of a buffer, in case you want to include that buffer out of county a little bit distance to capture more information. So we're going to define that function, and you can see at the bottom, this is what it returns. It returns our county, our geodata frame of academics, and a table. The operations in here are ones we've all talked about. So we're filtering the county data frame. We are using our buffer argument here. And then we're making sure the projection systems match before doing a spatial join between the data frames, but only for the single county. So that's how we're going to limit our output. Then we're going to create the pivot table. Let's see how it looks. So if we look at just the pivot table that's put out, you can see we've got Yolo County specified in our argument, and we can see how many staff there are per position. Hooray! I mean, it's useful, right?
Now, why do you need that buffer?
You don't really need a buffer. I think we threw it in just to include a spatial operation. You could use it if you wanted. Yeah, some of this is, of course, just for demonstration purposes, right?
Thanks.
Yeah, no problem. Next, we're going to make a handy dandy chart. And since this is for each county, it's going to look a little different. It seems kind of silly to have a stacked bar chart for one county alone. So this will turn it into a single county bar chart. Here, we're going to pull the county name from the pivot table. And I don't expect you guys to know instinctively all of the grammar in this code, but they are definitely commands you can copy and paste into your own work and replace different elements. We're going to use a command called transpose, which actually just switches the columns and the rows. This is something you can do in Excel, and I'm sure you've done before, but kind of handy. But for producing bar charts, it's pretty useful. And then, yeah, we're going to create this little bar chart of Yolo County academic positions. And you can see here, we have each position title and the number of employees per position. Let me see if there's anything else particularly interesting in this, the grammar of this command. There's the transpose, there's the plot. Again, it's kind of cool to use this F command so that we can have the county name change depending on what pivot table is provided. So I think that's pretty cool. I've done a lot of making graphs in my day, and boy, it gets really boring editing axes manually. So yeah. Finally, I think there's two more. There's summarized location. So this gives us the number of academics and the number of employees per location in the county. So this is a spatial, this is not a spatial frame. This is what we're going to use to make our graph, our map. So it is spatial. It has our geometry column, and it tells us the number of employees and the number of titles. So this we generated early on as well. And it just takes one of the arguments from our previous functions. And then finally, a mapping function. So it takes our single county geometry, this summary table, and then you can say if you want it to be dynamic or not. And if you say dynamic is true, it'll run this dynamic map. And if you don't say it's true, it will create a static map. So we'll go ahead and run that. And we said, interesting, we said false. Oh, it needs one more argument. Sorry. There we go. And then false. I broke it, everybody. This is what we do here.
We break it, but you will fix it. I know that.
Yeah, well, we'll run it for now. Looks good. That's interesting. Okay. False. Now we are going to chain functions. So this is like where it gets really cool. We already knew that we could run this command to get
Yeah.
these data frames and to change them. So here we go.
Can we up on that summary function where you change that the previous one where you change that false? So okay.
Yeah.
So summary x is equal to so you remove that, right? The cells.
You can leave it for now. It's just going to
Oh.
use the default for the second argument too.
Okay.
I don't know. I'm gonna fix it later. But yes, you can
Yeah.
leave it for now. It should work. Okay.
Okay.
So here we're going to combine our functions. So this is like a very basic, we're going to run our sample function for Alameda County, and you can put whatever you want for the buffer, 0, 50. I wouldn't make it very big. Then we're going to run our position chart, our summarized location, and our map selection. And then just in this one cell, we can generate all the figures we needed for our report, right? We should print the chart too. Might have to add one more cell to print the chart. Anyways, so it's pretty handy. And then here, I've created a cell where you can run one on your own. So replace the county argument, Alameda, here with whatever you want, and then it will replace it in the function. So I'm going to change it to, what's a cool county?
How about Mendocino County? I'm partial to that.
I got to spell Mendocino correctly.
Uh-oh.
Uh-oh. Uh-oh, she broke it. I don't think I spelled it right.
An OF, not there you
go. Put Merced.
It's not a spelling training. Okay, so then it's just going to regenerate all our stuff for the county we specified. That's a time saver, right? So yes, if you can spell a county, you can run it for whatever county there are ANR locations in. So even if you're just running, if you've created functions for like buffering or for clipping or things like that, you can string commands like this as long as the arguments go together, like in your functions. And you can replicate whole workflows pretty easily, which is really cool. And now, this is like our last super crazy level with this function thing. We're going to add one more element, which is called a for loop. And a for loop takes a list or a series of objects, and it says, for each item in this list, we're going to run through whatever the next thing is. So here we say for county, in a list of counties, run all these functions. And here at the beginning, we define county list, and I do that as in our ANR counties data frame. How many, take all the unique values of county name and make them a list. There are a lot of them, and I don't want to do that to you guys, so I have filtered it down to just 4 of them in this next command, but you could run it for the whole thing. Now, the other element here is that this is actually going to do some admin for us. So this is going to create a folder in our little GeoPython folder, session 3 data folder. It's going to create a folder called figure folder, which I'll delete now just to prove it's going to make it. And then it's going to, for each county, make figures for that county in its own little folder and save it for us. And it's going to save them as the chart as a PNG, the map as a PNG, the summary table and the pivot table as Excel files. So the commands for the maps are .savefig, and the commands for Excel is to Excel. And we'll see if this works. Our 4 counties are Alameda, Santa Clara, Contra Costa, and Yolo. And at the end, I told it to tell me where it wrote them, just so I can make sure I can find it later. This is a very healthy thing to include in your commands, and it ran it 4 times because it ran through this 4 times, right, in our for loop. And it still shows us the figures, which is kind of nice. We can see that it worked. Made us little static maps of each county and our charts. And then here, I swear I deleted it. Here's a new figure folder that was just created, and it made one for each county. And in each county, it's got our 4 figures. So this is really cool if you're making presentations or if you're doing things that are repeated. Very handy. because sometimes you don't want to try to copy and paste things or screenshot them from a Jupyter notebook. You want them written somewhere practical. So that is an example of kind of stacking functions and using for loops to run through them iteratively. So I know that was a lot to take in. I think this is kind of a high level concept, but I didn't want to just do exactly the same thing as the last session. Yeah, and let me know if you have any questions. The last section is on exporting. So maybe I'll go through that, and then at the end, if anybody has any questions, I'm super happy to go back to stuff. So we just did some exporting. Surprise. We covered pandas saving to Excel and matplotlibs saving figures to PNG. So these are the commands. You put your data frame to Excel, your figures save fig, and then for CSV, which we didn't do in this example, it would just be .csv. For spatial data, we're going to go back to GeoPandas. And so the default is very simply gdf.toFile. So you put the name of your geodata frame and then toFile, and then the information about where you want that file saved and what type. So there are different drivers for some formats, but here's an example. For shapefile, you're just going to do geodata frame 2_file and then call it a .shape, and it'll save all the components of your shapefile. For geopackage, you just need to specify the name and the .gpkg. There's a driver associated with that, and you can name the layer as well. And then GeoJSON, again, just toFile, .geojson, driver, GeoJSON. Frustratingly, Python cares a lot about cases, so make sure you get your cases correct. And you can even do it to an ArcGIS geodatabase, but the geodatabase does have to already exist. But you can write as a feature class. The path is the path to the geodatabase, and then the layer is your feature class name. So let's do one. Let's write our YOLO County data to spatial format. We're going to create one more folder called spatial outputs in our very tired little data folder here. So in session 3 data, if you run that, now you'll have a spatial output folder. And here we go. Wow, that was quick, right? We did our shapefile, we saved County Academics as a geo package, and we saved it as a GeoJSON. You could change the county and run it again, and it would do it again for a different county, which is pretty amazing. Let me see. Now, you may be asking, or you may not be asking at all, what about these nasty little multiple geometry column data frames we created earlier? Because we wanted to feel powerful and in control of all our data and have them all in one table. Well,
Yeah, yes, Janelle. What about all those lines?
Yes, what about them? Well, fun fact, it's really, really not great to write all of those to file as a spatial data frame. It's going to be much better to pick one at a time and write that as a file. So I recommend dropping all but one geometry column, renaming it geometry, and then writing that file. So it's less fun, less exciting, but you can always join your other geometry back in again later by the index. But here we go. You can use the .drop command with all the column names you want to get rid of. So here we're going to drop county, location, and location buffer. And then we're going to write our sad little single geometry file as a geo package. So here we're writing the centroids to file. You can see here, now we only have one spatial column, and it's written. We wrote it out using toFile, and we wrote it as a geo package. It's sad, but you know, you can't always stay in the environment. I think there are a couple formats that can handle multiple geometries, maybe Parquet, but that's a topic maybe for office hours. A lot of formats can handle, like shapefiles can actually handle multiple geometry columns, but only one of each kind. So like 1 point column, 1 line column, 1 polygon column. But I haven't played with that. I just have read that. So take it with a grain of salt. Best practice, pick one geometry column, write using that. Now, if you are really working with like a text-only situation, you can use what's called well-known text format to rewrite geometry as like strings, which is just text. And that's kind of funny, but you can do that to write data as a CSV. hopefully you're not doing that very often, but what may happen to you is you may read in data of this format because somebody else has done it. So here we're going to copy our academics data frame. We're going to take this geometry column and we're going to say, convert it to well-known text.wkt and then write it as a CSV. So it should be in our spatial folder, which I just didn't click on. And then county academics CSV. Yeah, it's probably good to not be the person who writes well-known text format columns, but it does work. Here it is. It looks pretty much the same, but it prevents the file from really messing with it in a way that's going to cause problems down the line. We're not going to save that. So you can then email that to your friends. And the other thing you need to email them if you do that is the coordinate system, because that is absolutely not saved with the CSV, but you can read it in using just pandas, read CSV. You can then tell it what the geometry column is. And then using from WKT, we're telling it the geometry is in a weird format. It will make you a new geodata frame. But you do need to set the coordinate reference system. Here I have set it. And again, this is our Yolo County points for locations. If I do not set the CRS, it's like really excitingly nowhere. So again, don't take coordinate reference systems for granted. Don't be that guy. We're better than that. Okay, so here I just tell it to set the coordinate reference system to match another data frame. And it does it, but you need to know what it came from to do that. Okay, wow, that was a lot of information, guys. Thank you for bearing with me. And I hope you can implement some of this and copy and paste some of the commands and at least like GeoPandas, buffer it up and have a good time with your spatial data. So thank you. Happy to take questions now.
Yeah, thank you. It's all of them work, so I don't have any question. Yeah, thanks a lot. It was really good. Very good.
Thank you. Well, I know ARC is like so, if you've grown up using ArcGIS or like learned academically using ArcGIS, thank you. It can be hard and kind of scary to work in a notebook format, but honestly, with the introduction of especially these kind of interactive explorer tools, I feel a lot better because I do, as a geospatial scientist, need to do a lot of these, I call them gut checks on how the spatial data was processed and if it was correct or not. So I think it makes it really accessible to a lot of people, and especially people who have Mac computers and can't use basic ArcGIS products. I think it's really cool. So
I would second what Genoa just said. And one thing that her notebook really illustrated for me was how well thought out the open source community is, especially with GeoPandas and this mapping functionality. It's so much harder to do with the Esri ArcGIS API for Python to get an interactive map and get everything working the way it's supposed to. And this is out of the box. It just does it. It's phenomenal. So Genoa, thank you for doing this. This is great.
yeah, share it with your friends. Go ahead, Prakash, sorry.
No, I completely agree with saying so what he said.
Yeah, and you can, there's really good implementation for rasters too, using a package called raster.io. So if you ever want to check that out.
Yeah, I use that often.
Yeah.
Any idea like when will be the next training for like processing drone data or the images taken from drone?
We will have to pass that to Sean. Is there a drone data processing workshop coming up, Sean?
Oh, there is not a drone data processing workshop coming up right now, but we have one on our YouTube channel. We're using Pix4D that you can refer to. So if there's a little plug for I just search UCANR-IGIS and in YouTube, and we have a channel with tons of videos there. And if you sort in order, it's one of the more recent ones. There's one on processing multispectral data with Pix4D, and then there's another one with using drone data in ArcGIS Pro that might be interesting to you.
Cool. And you use Python, or what language do you use there?
Oh, it's entirely using GUI off the shelf. First photogrammetry applications like, well, in this case, Pix4D Mapper,
Uh-huh.
and then just working with the data in ArcGIS Pro.
Okay, so Pix4D combined with the desktop GIS, correct?
Yes, correct.
Okay. Cool.
While I'm chatting, if you could please fill out the workshop
Yeah,
evaluation.
I'm doing that. Yeah.
Okay, great. I
Thank
just
you.
put it in the chat.
Thank you. Um,
And since there's just a couple of you, I might not
Yeah,
need
yeah.
to email it out.
But we
Yeah.
appreciate you guys coming. Again, this is a new workshop series, so
We're
it's
going to
hard.
continue session 2 of the
Sorry, what was that?
What was that? Uh-oh.
No worries, he might be on the phone. Session 2 is on the workshop YouTube channel too, I think. Yeah, which is
Yeah,
cool.
that's correct. And this one will be up on the YouTube channel sometime early next week.
Yeah. I've been doing a decent amount of raster work in ArcPy, and that's been working pretty well, Prakash. But I would love to go back into raster IO. I am just limited by the requests of my client. So, but looping functions for that is really, really powerful, I think, because you can just like clip your raster data so easily.
ArcPy, ArcPy is like is programming language like Python, or is it like a desktop environment?
ArcPy is really, it's ArcGIS Pro with Jupyter Notebooks. So instead of the
okay.
ArcGIS API, which is very tied to the ArcGIS online system,
Uh-huh.
it's really all your like favorite ArcGIS Pro commands.
Okay, okay.
Yeah. So if you already have that, it's fairly handy. Yeah. Happy to chat about that sometime.
Yeah, I would second that. The nice thing about ArcPy, which we didn't get into in this series, is that if you're familiar with Pro and you can run commands directly in Pro, you can get the commands and then you can easily modify those commands to work in for loops and everything else. It's really quite nice for that.
But I'm not sure it's better than raster IO. Honestly,
Correct.
The building functions and looping capabilities from any coding language, I think, is really what makes it powerful. The only reason Arc, I think, stands on its own some reasons is for some points is like if the data is already in a geodatabase format, or if you have to make a bunch of like SQL queries. The way they store data is pretty efficient if you're working in their ecosystem. But if they're not, there's like really, really great open source packages. So don't limit yourself.
Okay, then. Thank you, guys.
Yeah, thank you. I guess we'll wrap up unless there are any other questions. But thank you for coming.
Yeah, bye.